Welcome to Beyond the Radio Dial, a wireless innovation forum podcast about the importance of radio spectrum for everyday life. I'm Stephanie Hamill, Marketing Director for the forum. Beyond the Radio Dial is hosted by Andy Clegg, WinForum's Chief Technology Officer and self-described spectrum nerd. Now, here's Andy.
Okay, well, thank you very much, Stephanie. Today on Beyond the Radio Dial, we actually have a special episode queued up, and I'm going to turn it right over to the Wireless Innovation Forum CEO, John Glossner. John, take it away.
Thanks, Andy. So in May, we held a workshop on artificial intelligence in wireless communication systems and spectrum sharing, and had a wide variety of papers at that. And today, we're very fortunate to have the best paper presenters to go over what was the key elements of their paper and answer a few questions. And this was joint research between CableLabs and Ohio State. So I'm going to turn it over to Mark Poletti to give a brief introduction about the background of the research and the information in the paper. So Mark, take it away.
Great. Thank you, Andy, John, and the Win Forum for the opportunity to be here to discuss our research. It's an honor to have our paper be selected as best conference paper. And to me, this showcases how well industry and academia can collaborate together, push the envelope of technology and learn from each other. So I am Senior Director of the Mobile Networks Group here at CableLabs. My team focuses on 5G, 6G activities, CBRS, and new spectrum opportunities. We focus a lot of many aspects of dynamic spectrum sharing, coexistence, sensing. We do a lot of in-house simulation and analysis, all things leading to how well we can efficiently and fairly share spectrum. So we all know one of the hot topics in the industry right now is dynamic spectrum sharing and integrated sensing and communication. And how this can fit into 6G, like AI native 6G, AI for spectrum management, joint sensing, 6G spectrum, and this aligns with the research here at CableLabs. So leading up to the research for this for the research paper topic at CableLabs, we've been working on our own platform to collect spectrum sensing data and develop techniques to analyze the data for channel occupancy. We view dynamic spectrum sharing to have three components: a detection sensing mechanism, an analysis prediction engine, and a mitigation resolution action to share the spectrum. So we have the detector or the sensor component. We also have the analysis component. And now we're fine-tuning our analysis component with prediction, and then we'll apply this to the various use cases, mitigation and spectrum sharing. And this is a long-term research goal of ours. And this is where we had the opportunity to work with academia and got to know Dr. Jenner and Jiayu from the Ohio State University, who have been researching various techniques of machine learning, including the application of spectrum occupancy prediction. This was a good fit for Jiayu's PhD research topic on machine learning applied to spectrum occupancy prediction and channel availability. And we were interested in what traditional machine learning techniques are being used, what new techniques can be used, what level of accuracy can be obtained, and what are the trade-offs of spectral occupancy prediction. So we collaborated with and sponsored Jiayu as an intern to do this analysis, and it turned into this multi-timescale transformer-based spectrum occupancy prediction for real-time dynamic spectrum sharing paper that was submitted to the WinForum AI working group. And again, this is an example of how well the academia and industry can work together to push the envelope of technology. So that's kind of the background of how this fits into CableLabs research and how it overlaps with Dr. Jenner's research with her group at Ohio State University. And I'll stop here and I'll hand it over to Dr. Jenner to introduce what her team does.
Thank you, Mark. Thank you for this opportunity. My name is Aylin. I'm a professor at Ohio State University. Actually, Jiayu is a doctor. She just attended her PhD thesis.
Congratulations.
Yay. And I've myself worked in wireless for much longer than I care to remember, over 3 decades now. Started as a student. And, even when I was a grad student, we had a center that closely collaborated with industry research organizations like CableLabs and so forth. And so I come from that background of finding, let's say, intersection points between the interests of industry and technology and fundamental research. As Mark nicely indicated, we found a common interest. And through Jiayu's leadership, we have been able to produce these interesting results. With respect to how this fits to our research program currently at Ohio State, we have a 60 and Beyond initiative that I have the fortunate, I've been fortunate to lead. And essentially, we look into what's going to happen in 60, what kind of technologies will make it into the next generation and beyond. And of course, spectrum sharing, in particular, dynamic spectrum sharing comes into play. And of course, coupled with the fact that we expect 6G networks to be AI native, a natural question to ask was, how do we use machine learning for spectrum sharing? And the first sort of component of that, as Mark had explained, is how do we better predict spectrum occupancy using machine learning? And this work is really about that. And so without further ado, I want to present Dr. Mao. To explain a little bit about the paper.
Yeah, thank you, Dr. Nurse. Thank you, Mark, for introducing me. I'm Jiayu Mao. I just did pass my defense last week, and my PhD research focus is on resource efficient, AI native, and energy sustainable for next generation wireless networks. And our collaboration with CableLabs is to discuss how can machine learning to be utilized to improve the wireless communication. And specifically, can I share my screen to introduce our best paper? Yes, thank you. Today it's my pleasure to present you our best paper award, which the title is Multi-Timescale Transformer-Based Spectrum Occupancy Prediction for Real-Time Dynamic Spectrum Sharing. And this is a collaboration between Ohio State and CableLabs. And here is the list of the authors. Next slide. Oh, okay. So let's start it. First, I would like to give you the broad pipeline of the entire project. As you can see from the slide, there are in total 6 steps in this spectrum sensing and spectrum sharing project. The final goal is to develop an AI native dynamic spectrum sharing. Step 6, we haven't been there yet. And what we have accomplished for now is the first 5 steps. The first step is to collect data from all the real-time locations, and then we will transfer this data to the server for the post-processing. For specifically, we do the channel occupancy for the processing, and after we get this channel occupancy data, we will construct a data set which can be later used for the learning or training. And then in step 4, we will select several models. It can be machine learning or non-machine learning, for example, Markov chain. And in step 5, we will utilize both data sets and models to do our next minute channel occupancy prediction. Here is the system that CableLabs have been developed for 2 years. We could see that there are several different multiple remote locations, and in each remote location, for example, in Ohio State, in our lab, we have one antenna that can passively detect the spectrum, and then this spectrum information will be scanned by a spectrum scanner. And this will collect the information as the way we want. For example, how much bandwidth and what is the scanning time interval, things like that. And this scanner will collect the data into the local computer, and this local computer will upload the collected data into an FTP server. The FTP server will then further transmit the data to a central server for further processing. And in the end, CableLabs also developed a dashboard to show the spectrum utilization for the external users. Specifically, in our best paper, we utilize this mathematical concept called channel occupancy. The red line is the threshold line, and which we borrowed from the Wi-Fi standards. And then this channel occupancy is defined as a very simple binary indicator. If the data is above this red line, then we consider the channel is occupied, and we set up the channel occupancy at 1. And if everything above, like below this red line threshold, then we consider that this channel is not used. Then we set this indicator at 0. So channel occupancy is a binary term that we utilize to construct our short-term data sets. And in our paper, we specifically focus on 2 months data, like May to June 2025. And the location is in CableLabs, which is in Louisville, Colorado. And it's the short-term data. We also further consider a long-term data construction. That's why we call it multi-time scale. Specifically, on the left-hand side, we draw a heat map for spectrum utilization. Specifically, this concept means how much spectrum is utilized within 1 hour. And then we grab first top 15 channels of this from this heat map, and then further develop hourly channel activity score figure. And for each hour we pick a median of the spectrum utilization, and then draw this activity score into 24 hours. And from this figure, we draw 2 right lines to separate day and night. And because it's a very initial step, we consider this long-term also as a binary indicator, which if it is 1, then it means daytime. If it is 0, then it means nighttime. And the duration we developed from the heat map is from 8 a.m. to 7 p.m. And so how we predict the spectrum occupancy? We utilize the 4 different machine learning methods: random forest, XGBoost, long short-term memory. Those are baseline machine learning methods we considered. And our contribution of this paper is to develop 2 transformer-based architectures: single input transformer and dual input transformer. For single input, we just use the previous short-term data. Well, for dual input, we combine both short-term and long-term, remember that day and night indicator, into this machine learning model. And then at the end of the day, we give the prediction for the next minute channel occupancy, whether the channel is occupied or not, given the previous k minutes historical data. And here is the numerical results illustration. This is 1 minute prediction. We would like to show you what it really means for prediction. This blue lines means the true data, which means collected from the antenna, whether this channel is occupied or not. And the yellow one is the one that we are able to achieve from the machine learning methods. And we could see that there are some errors. For example, if it is idle, but now our predictor thinks that it is occupied. So as a result, we are able to achieve some level of the test accuracy. And specifically for May and June, we could achieve on average 86% test accuracy for all the machine learning methods, and outperforms the previous non-machine learning statistical Markov chain baseline. And we also compared the complexity comparison for all different methods. We all know that machine learning is good, but how much it will cost for the machine learning training. And here it's the server information, and we could see that For random forest, it will take about like 5 minutes, and it can only be run on the CPU, where the shortest is the LSTM. But however, it's not an apple-to-apple comparison, because for LSTM and transformer, both of them are running on the GPU. And of course, we know that GPU has more powerful computation power to run the machine learning. As a result, both of these like neural network based methods have can achieve relative short time, especially for LSTM. It's only about 30 seconds. And we also develop more results for this problem. We consider how many minutes from the historical data can be useful to predict the next 1 minute. And we did for 1, 5, 10 until maximum 60 minutes. And we could clearly show from this graph that the test accuracy didn't achieve too much higher when we consider more historical data. And interestingly, from this figure, we could see that random forest even kind of have a little bit degradation from this training performance when we include more longer history. And here is the conclusion of our paper. We would like to show that our machine learning methods can achieve about 86% test accuracy, and since performance differences are very marginal, everyone is very similar, we would recommend random forest. And specifically in this work, we developed 2 transformer models, both single input and dual input. And we show that transformer architecture is promising in this specific spectrum occupancy prediction problem. And later we could even consider more multi-time scale. And for now, we only consider a binary indicator to separate day or night. And for future work, we could consider more different dynamic temporal features and multi-step forecasting and even larger data sets. And remember that the long-term goal is to integrate our spectrum prediction into the AI native dynamic spectrum sharing frameworks. And that's all for my introduction for our best paper.
Thank you, Jiayu. So we can take questions. I guess I just wanted to chime in my excitement. What's really interesting to us in the study is it's not a theoretical study. As you've seen, it's actually collected data. And based upon the data itself, we are running these machine learning methods. And if you have a GPU, you could do it quite fast,
yes,
even with the transformer methods, and we're getting real results. Even if they're preliminary, it's a direction that's very promising to me anyway, because of this realistic part of the work.
Yes.
Yeah, and so one thing I think it would be good to point out is that there's a lot more detail in the paper. And so encourage you, I was at the presentation, there was a lot more detail there. Here we're kind of covering just the highlights of that. And well done. I think, it was a very interesting paper. Because it used real data, we have a kind of sense of, are there really occupancy issues? And one of the things that I recall from the initial paper that is in your results from today as well is that even though your accuracy score might be 85%, if you're an incumbent, it covered every case that an incumbent might be in that particular band. And it was maybe a little bit overprotective. But I think from the point of view of sharing with incumbent space, that's an important point. And I don't know if that's really the research aspect of it, or maybe more like the CableLabs aspect of it. But for either of you, if you can maybe make a comment on that kind of commercialization capability, that would be great.
Absolutely. I mean, from our end, that's actually consistent with at least what I know from the current sharing mechanisms, even regulation-wise, is that we are leaning towards being a little conservative in terms of the incumbents, just to make sure that they have their rights. Now, is that going to be the case in the future? You tell me, right? But the nice thing about this research is it can nicely adapt. And it is data driven, therefore, there are no sort of underlying rules that tell us you have to do it this way or that way. You could put it in, but you can also remove it and leave it to the data. And as we get more and more high quality data, we can actually build better ways of utilizing that data in constructing models and then integrated with the control decisions of allocating the channels.
Yeah, I was just going to add fast is that one of the big things that takeaways that I had was just like you're saying, the accuracy of the data, or the how well that data is before it goes into the machine learning engine. And we learned a lot, and Jiayu, you can elaborate more on this, but grooming the data or shaping the data before it goes into the machine learning, that was a big, which is obvious, but it's kind of tricky to learn and understand what's good data and what's not good data. And also, the one thing we also learned was, and we knew this going into this, was there's a lot of trade-offs in the way the data is collected in terms of the scanning rate and the threshold and the resolution bandwidth. So that's kind of future work, but that would help. We talked a lot about how that could improve the accuracy of the machine learning technique. So I don't know if you want to elaborate any more on that, but Jiayu, but that was a big learning.
Yes, thanks for adding the details, Mark. Yeah, like you kind of reach a very critical part. Like as I mentioned, like our first step is to collect all the raw data. However, it's our job to understand what is the real world data. And so far, what we have done is we set up all the threshold, resolution, bandwidth, and the time interval, like the scanning frequency, manually. However, whether this can and we already kind of have some initial results, realizing that all these setups will influence our prediction, because it will influence how we post-processing the data, and then this directly controls the quality of the machine learning data sets, which of course will influence the prediction accuracy. So this is kind of one of our direction is to develop how can all this setup from the data collection can influence the machine learning prediction, and from the prediction results we could develop how much exact data requirement that we want. So this is kind of a back and forth effort. So from the beginning, we didn't know anything, and we just manually set up a group of parameters, and now we have some initial results. We want to improve it, and then we need to go back to this initial setup to further develop, to do the research. Yeah, this is the entire research solution or process.
So there are a lot of different machine learning algorithms that can be used. Maybe you can just tell us a little bit about why you picked the class of algorithms that you did, and if you experimented with some others that maybe just didn't work and didn't make it into the paper or something. But just give us a little insight into these machine learning algorithms and why they were useful.
Yes, that's also a good question. Initially, when I created this problem, I do think about what machine learning algorithm I should pick. So I just go back to my textbook, and random forest and XGBoost are the very initial non-neural network, very simple, very low complexity, very naive machine learning models. So I was thinking, if this type of models can work, then we directly go for it, because we also from from the during my internship in CableLabs, I also realized that the real world deployment also have many limitations. So in our academia perspective, of course, we want fancy models. For example, the transformer, the neural network, all the complicated fancy machine learning models. However, this from the communication industry perspective, I learned from Roy and Mark that all the base stations actually have all the power limitations, and the network also have the latency. So we may need those simple as possible model to be able to in the future really equipped or deployed in the real world system. That's why from the beginning I test the random forest and XGBoost, and then from the academic perspective, from me and Dr. Yaner, of course, we are more interested in more complex models, more advanced AI models, whether this can also work for this specific spectrum occupancy prediction problem. And then that's why we pick LSTM, that's a neural network architecture. And later, in this best paper, we also want to test whether the most popular machine learning model transformer can be utilized into this specific problem. And specifically, the more powerful of the transformer can also have the more complexity regarding to deal with the more complex data. And also, of course, that's another future direction to develop more complex machine learning architectures. But from the beginning, how we develop the machine learning algorithms is following from the very beginning, practical sense, and then more and more step by step to the academic perspective.
I guess one more thing I would add to this is transformers indeed were a good natural direction, just because we're looking at temporal data and we're trying to understand the correlations, and that's a way that modern AI creates context and correlation. So it was a natural way of, other than searching for fancy models. That was kind of the nice next step in terms of the work.
Did you try this out at more than one sensor site, or is the bulk of the work done at one of the sensors? And if you did try it at different sensor sites, did you see significant differences in performance from sensor to sensor?
I think mainly it's from the Colorado site that we have so far, and I think there's more to do in terms of processing data from other sites. There will be geographical differences too. And that's another way, I think, in the future to think about these architectures like transformers, to think about, how to extract and learn those correlations and utilize them. So definitely so this wasn't, but it's a very important direction to see which of the sites make sense together to create a data set.
Yeah, we were thinking about that too, and Jiayu, you can talk more about this too. Is maybe some machine learning methods are better at certain types of data than others, right? Which would lend itself to maybe certain type of machine learning method is better at a Colorado site versus a California site, or it depends on the activity, more active or less active site. So we didn't get that far, but that's another direction to go.
So Mark sort of touched on this earlier, but one of the very interesting aspects of your paper is the feature engineering that you did to build your database. And particularly something I hadn't seen before was you categorized the data into day and night, and that seemed to help your predictions a lot. Do you have the inspiration that gave you that idea, or how did that come about?
Oh, that's a very good question. Actually, this relates to your previous question, how I choose or design these machine learning models. As Professor Yaner mentioned, transformer itself is a very a good model to like explore the temporal dependency or correlations between all the sequence data. And from the real world measurement, we need when we think of like when we get rid of all these technical details, when we think about from the very beginning, we think that, for example, like in the daytime, the like spectrum at this band should be the utilization should be different at the nighttime, because, for example, everyone is sleeping during the night, so there will be less spectrum usage. And also this matches the like heat map that we observed from the spectrum utilization. Then like a very natural thought is to how can we like formulate this multi-time scale. So it can this is a very initial step. So far, I just divide the time into day and night. It can also be like weekdays, or like even into 24 hours. So each hour of the spectrum usage can have like different its own model to predict. So that initially that matches our intuition that to include more information will give us like better prediction accuracy. That's how, and then, so from the very initial step, I also would like to explore the very simple version. So that's how I decide to develop the data for long-term and just as a binary indicator to separate day and night.
Great. So it sounds like now that you're a doctor, we'll be able to see many, many more papers coming from you and your group on this topic. And I think it was really interesting. Andy, I don't know, did you have some more questions?
No, I think I'm good, and thank you all very much for the presentation. It's very interesting, and we should have mentioned earlier, CableLabs is a member of the Wireless Innovation Forum, which we thank which we appreciate very much. And we really like, one of the things we like to do at the Wireless Innovation Forum is help connect some of the academic research and industry research that's going on with current applications in the wireless world. So this plays right into this, and that was the purpose of holding this AI workshop workshop where we had the competition. So I think this worked out quite well. So thank you all very much. Congratulations on your PhD, Jiayu, and hopefully, yes, as John says, we'll be seeing many papers from you in the future.
Yes, thank you. I really appreciate that.
Okay, thank you all very much.
Thanks again, John and Andy. See you guys.
Thank you.
Thank you.